Hi everyone, so in this video today, we're going to answer question 2, this question here, from the Edexcel 2018 A-Level Paper 1 Pure Maths exam. So we're going to answer this question 2, and this question 2 is a differentiation question, and also a bit of stationary points involved in part B and C as well. So that's going to be our plan today.
But before we get into today's video, please do make sure you do click like and click subscribe. Click that like button, click subscribe. It really helps me out and it's free. It doesn't cost you anything and it takes you less than a second. So please do click those buttons and we'll get into today's video now.
So we have a curve C with this equation here, y equals x squared minus 2x minus 24 times root x. And we're told here that x is greater than 0. Just a little word about why that's got to be greater than 0, this x there. Because obviously when we take a square root of a number, we've got to ensure that that number within the square root is greater than 0 for the purposes of A-level maths. I mean, if you do A-level further maths, or if you study maths or physics at university, you will obviously be dealing with complex numbers at some point, where you can take square roots and negative numbers. But in A-level normal pure maths, we don't worry about complex numbers. So with these questions, we always use real number variables, so numbers which are basically on the number line. That's what we use in A-level maths. Okay, so the first part of the question is to find dy by dx. So part A, part I. We're going to differentiate our curve. So the equation for a curve, so x squared minus 2x. Sorry, let me just write that again because my pen lagged a little bit of that. Minus 2x minus 24 root x. Now, let's just make a note of this before we go any further, that the square root of x is the same as x to the power of a half. So when we do differentiation integration, it's always good practice to convert your square roots, so your square roots of any variables, into powers, into actual real powers. So in this case, we know that the square root of a number is the same as a number to the power of a half. So we'll just write that there because it's just going to be helpful when we do our differentiation calculation, which we'll do right now. So we're going to differentiate. So the way differentiation integration works is you differentiate each term individually and then you just combine them all, either add them or take them away. I mean, we got two minus signs there and there. So we're just going to differentiate x squared, then take away the derivative of 2x, then take away the derivative of 24x to the half. And the reason, I mean, the mathematical reason for that is because differentiation and integration, they're called linear operators. I mean, you don't need to know anything about that for A-level maths, but when you differentiate and integrate functions, the sum of the derivatives of each of these individual terms is the same as the derivative of the entire thing. But again, you don't really need to know that. All you need to know is you differentiate and integrate each individual term individually and then just sum them all together. So we're differentiating x squared, and then we're taking away the derivative of 2x, and then we're taking away the derivative of 24 x to the half. That's basically what I was trying to say there, but it's not really an important point for A-level maths. So differentiating x squared, we get 2x. So remember our technique, bring the power to the front, take away 1 from the power. Differentiating 2x, we just get the number 2, so minus 2. And then differentiating this 24x to the half. So remember, we're differentiating with respect to the variable x. Bring the power to the front, so we get minus 24, and then times by the power, which is half. And then we've got the variable x, and then we take away 1 from the power of that variable. So half take away 1, 0.5 take away 1 is minus 0.5, which is minus a half. So we get that there. So you got 2x, and then take away 2, and then 24 times half. Half of 24 is 12. You get 12 there, and then x, the minus half there. So that's going to be our final answer for part 1 of part A. If you really wanted to, you could actually write it like this. So 2x minus 2. And then what you could do is you could write minus 12, and then x to the power of negative half. I mean, let me just try and squeeze this up here. So x to the power of negative half. So from GCSE maths, hopefully you remember that this is the same as 1 over the square root of x. So when you've got a negative number in the power, you just basically take the reciprocal of your variable there. So make it 1 over, and then x to the power of a half is the square root of x. So you've got 1 over square root of x. So this is 12 times 1 over square root of x, which is the same as 12 over square root of x. If you really wanted to, you could write that, but either one of these solutions there will get you full marks. Okay, so now we're going to go to part 2 of the question. So now this part there. So now we want to find d2y over dx squared, which just means differentiate again. So this notation just means we differentiate our derivative again. So now our d squared y over dx squared is just differentiating our result that we got before in part 1 of the question. So we're going to differentiate 2x minus 2 minus 12. And then actually, to be honest with you, this like second final line, I mean, I'll call this A there, and I'll call that B there. We're going to use this capital A line here, because again, when we differentiate and integrate, it's just easy to have the powers visible to us. So in this case, this negative a half there. Because then it's easier to know what we're doing with our differentiation method. So then we've got so we're going to differentiate. Oh, sorry, my pen's lagged a little bit again. So we're going to differentiate 2x first. That's going to give us 2. We're going to differentiate this. Well, we've got a minus sign there, and then we're going to differentiate the number 2. When you differentiate a constant with respect to a variable, you just get 0, right? So the gradient of a number is just 0. So if you think about a graph, if you sketch the graph y equals 2, so this is the graph y equals 2, that's 2 on the y-axis there. The gradient is obviously 0. So when you differentiate a constant number, any of these constant numbers, these horizontal lines, you get 0. That's kind of the reason behind that. Okay, so we've got 0 there, and then we're going to differentiate minus 12x to the power minus half. Same technique as before. So we've got the minus 12 constant there, but then we're going to bring the power to the front. So this negative half to the front. So we're going to multiply minus 12 by minus a half, so minus a half in that. And then we've got our variable x, and then we're going to take away 1 from the power. Now, minus a half take away 1, so minus 0.5 take away 1 is minus 1.5, and minus 1.5 is the same as minus 3 over 2. Okay, so we've got 2, and then take away 0. I mean, we don't need to worry about that. Then we've got minus 12. Remember, we've got a time sign in between there. Let's just be careful about that. So minus 12 times minus a half. So negative times a negative positive. Half of 12 is 6. We get a positive 6 there. And then times by x to the minus 3 over 2. So that would be our final result for our second derivative for this curve there. Again, if you really wanted to, and I'll just do this here, you could rewrite this 6x to the minus 3 over 2 in terms of a surd. So if you wanted to, you could say, well, this is the same as 6 over the square root of x to the power of 3, if you really wanted to. So remember, if you've got a number x to the power of 3 over 2, that's the same as the square root of that number to the power of 3. Now, if you put the minus, the negative in the power, sorry, just rub that out there. If we put the negative in the power, minus 3 over 2. So remember that a negative number in your power just reciprocates your variable. So now what we're going to have, this is going to be the same as 1 over the square root of x to the power of 3. Okay, so you could write the final answer like this, or you could write the final answer like this there. Okay, so that's part 2 done. So now we're going to go to part C. So we're going to verify that C, this curve C, has a stationary point when x is 4. Okay, so first of all, if we're going to answer this question, we need to know what a stationary point is. So let's just make a note of this so we don't forget. So a stationary point is a coordinate. So it's a coordinate, and I'm just going to call it x, y. Actually, no, I'm going to call it AB. Let's just call it AB. So it's a coordinate AB such that, and when in my videos, when you see ST, it just means such that. So a stationary point is a coordinate AB such that the derivative, so when you differentiate your curve y with respect to x, such that dy by dx is equal to 0 when x equals a. That's what a stationary point is. So a stationary point is either a maximum point, so it could be like a maximum point like that, where the gradient there is 0. It could be a minimum point like this there, where the gradient there is 0. Or it could be a point of inflection, something perhaps like this, where again, your gradient there is 0. So that's what a stationary point is. So it's good to know what a stationary point is in order to answer a question on what a stationary point is. So we want to verify that this curve has a stationary point when x equals 4. So we know dy by dx. So we know that dy by dx is equal to what we found in part 1 of part A. So this result there. So I'm just going to copy this out again. So 2x take away 4. Sorry, 2x take away 2. And then we've got minus, it was 12, wasn't it? Yeah, minus 12 over root x. So we've got minus 12 over root x. Now, if this x equals 4 gives us a stationary point, so the question wants us to verify, so to check that we have a stationary point when x is 4. So if we have a stationary point when x is 4, that means that dy by dx must be 0 when x is 4. So let's again make a note of this. So if x equals 4 is a stationary point, stationary point, then when we sub x equals 4 into dy by dx, we need to get 0. Okay, that's what we need. So basically the question is asking us to check. So when you see this word verifying questions, we don't need to do any like proof or any show that kind of stuff. We just want to check. So check that when you plug in x equals 4 into our dy by dx, do we get 0? So let's have a go doing this. So we've got dy by dx, and we're going to plug in x equals 4. So when you see me write this notation, dy by dx, and then some brackets next to it, just means I'm plugging x equals 4. So we're going to take our dy by dx. We've got 2 times x, but x is going to be 4, so we're plugging in 4. Then we've got minus 2, and we've got minus 12 over root x, but x is 4 in this case. Okay, then we're going to do our calculation. 2 times 4 is 8, take away 2, and then take away 12 over the square root of 4. Square root of 4 is 2. Okay, so we've got 8 take away 2, which is 6. We've got 12 divided by 2, which is 6. 6 take away 6, as we needed, is 0. So therefore, x equals 4 gives us a stationary point. So that's how you would answer that one. So with verify questions where it says verify something, we just want to plug in the number and check whether it gives us the result we needed, which in this case is 0. There. And another thing I'll mention as well. So remember, when you square root a number, so for example, square root of 4 is always positive, square root of 4 is always 2. So the square root of a number is always a positive number. Sometimes students get a little bit confused because, for example, with equations like x squared equals 4, there are 2 solutions. You get x equals 2 and x equals minus 2. So some students think, well, when you square root a number, you get 2 answers. You get a positive number and you get a negative number. So let me just make my equal sign a bit neater. So I actually just write this again. So when you solve quadratic equations, usually you get 2 real solutions like this one there. So what I was saying is that a lot of students think, well, okay, when you square root a number, that means you get a positive number and a negative number. No, that's not correct. The square root of the number is defined to be always a positive number. But when you solve these equations here, you can have a negative number solution, because when you square a negative number, you get a positive number. So there's a little bit of a nuance you just got to be careful with. So square roots of numbers are always positive, but because you can square a negative number and get a positive number, when you solve quadratic equations like this, you're going to have a positive and a negative solution. But that doesn't mean the square root of 4 is negative 2 or positive 2. Square root of 4 is always positive 2. But when you solve x squared equals 4, you've got positive 2 or negative 2 as a solution. So just be careful of the distinction between the two. Anyway, right, back to the question. So part C. So now we want to determine the nature of this stationary point. So remember, when we determine the nature of a stationary point, we go to our d2y over dx squared. So we've done the hard work already, really. We've worked out this d2y over dx squared. That's going to determine what our stationary point is. Is it a maximum? Is it a minimum, or is it a point of inflection? So part C to the question. So I'm just going to copy out d2y over dx squared again. So we know from part 2 of part A that it's this here. So 2 plus 6 times x to the power minus 3 over 2. So 2 plus 6 times x to the power minus 3 over 2. So again, similar to the part B of the question, the previous part we just did, we want to plug in x equals 4, right? So we've got a stationary point at x equals 4. We want to plug x equals 4 into our d2y over dx squared formula. So let's sub this in. So sub x equals 4, and let's see what we get. So we get d2y over dx squared is equal to 2, and then plus sign, and then number 6, and then 4 to the power of minus 3 over 2. Now, as we said in part 2 of part A of the question, so I'm just going to write this down here because I'm running out of room. This is the same as 2 plus 6 over the square root of 4 to the power of 3. So this is going to be 2 plus 6 over square root of 4, which is 2. 2 cubed is 8, so we get 8 there. So we've got 2 plus 6 over 8. 6 over 8 is 3 over 4, which is 0.75. So we're going to get 2.75. Now, remember when we determine natures of stationary points, the key is the second derivative, so is this d2y over dx squared greater than 0, equal to 0, or less than 0? So our result here, our 2.75, is bigger than 0. It's a positive second derivative. So the way that I think about this is that what this is telling us is that the acceleration, the quote acceleration of our curve at x equals 4 is positive, right? So what that means is that we have a negative, sorry, not a negative, sorry, we have a minimum point at x equals 4. So the kind of way that I think about this, so we've got x equals 4 on our curve there. This is our x-axis there. This is our y-axis. So we've got this point, this kind of stationary point. Let's just pretend it's down there. Now we've got a curve like this. So let's just pretend that this is the minimum point. So when you're at the minimum point there, so imagine this is kind of like a roller coaster. This is how I think about it. So you're going along this roller coaster, and then you get to the minimum point there. Your acceleration is positive. So in other words, because you're at your minimum point there, you're about to move upwards. You're on the verge of moving upwards. So your second rate of change, remember the gradient is the rate of change of your curve. The second derivative is the rate of change of your rate of change. So in other words, the acceleration of. So if you imagine that your y-axis is the your acceleration. Sorry, not the acceleration. Sorry, your displacement, your distance traveled, right? And you imagine that this is time here. Your x-axis is time. So you kind of got like a distance time graph. So the idea is that because you're about to move upwards, you've got a positive quote acceleration. So here at this minimum point there, d2y over dx squared is positive, even though the gradient there is 0. So the gradient of the curve there is 0. So the speed of your curve here is 0. But because you had a negative gradient there, so a negative speed, you then approach a 0 speed here, a 0 gradient. That means your acceleration is positive because now you are on the verge of a positive speed, a positive change, rate of change. Hopefully that made some sense. I mean, you don't really need to know the ins and outs of that, but hopefully that kind of justifies why on a minimum point, your d2y over dx squared is positive. So what this is telling us is that therefore, sorry, let me just get my pen to load up. There we go. So that means that therefore, since d2y over dx squared is positive, that means that x equals 4 is a minimum point. So I mean, really in reality, you should call it a local minimum point. But in A-level maths, you can just call it a minimum point. So minimum point. So the reason why technically it's called a local minimum point is because you could have a curve like this. You could have a curve which goes like that. So with this, well, this is like a cubic curve here. So that would be called your minimum point there. But obviously this point there is not the minimum point on the entire curve because you've got like tiny points down here, which are even more minimum than this minimum point there. So we call it usually, I mean, the technical term is a local minimum. Because locally in this like local region like here, this is the minimum point of this region. So we call it a local minimum, but in A-level maths, you can just call it a minimum. You don't need to worry about this local word. So yeah, the nature of that stationary point is a minimum point. So any questions, do leave a comment below. And remember as well that if your d2y over dx squared is negative, then it means that, of course, you have a maximum point instead. And again, the way that I think about this, if you have a maximum point there, you're traveling along this roller coaster. So when you get to your top of your roller coaster like this, your acceleration is now negative because you're about to go to a negative speed. So again, imagine this is distance. Imagine this is time. The gradient of a distance time graph is speed. So in this region here, you've got positive speeds, positive gradients, and now you've got a zero gradient, but your acceleration's negative because you're about to go to a negative speed. So obviously, if you're on the verge of going to a negative speed, your acceleration is negative. So think about this second derivative as an acceleration. That normally is a good way to think about it. It kind of helps you realize whether being bigger than zero, it helps you understand that being a second derivative being bigger than zero gives you a minimum point, and a second derivative less than zero gives you a maximum point. But any questions, please do drop a comment, because obviously I want to make sure you guys understand all this stuff. So yeah, thanks a lot for watching today's video.
If you are interested in having an online maths tutor for either A-level maths or GCSE maths, please do email me, because I am available to help out. So my email is drdifferentiation@gmail.com. So just drop me an email, just drop me some details about you, whether you're doing A-level maths, GCSE maths, and if there's any specific areas of maths that you need help with. So drop me an email, or get your parents to drop me an email, and then we can discuss everything about price, etc., etc. So drop me an email and we can get sessions booked in.